Okay, let's get going. So I thought we'd start with any questions. Anybody have any questions? So there wasn't too many people that responded to the review session PCQ, but maybe you weren't, sort of aware of it or whatever. But so I prepared a few things. But yeah, so questions. Yeah, so that's a tough one to field, right? I mean, I'll definitely go over everything that we've had a chance to do. Like one, for instance, like what I have today set up is just, I was going to go over some of the harder questions from the quizzes. So definitely I would go over the quizzes and make sure that you kind of see what you, the things you might have missed on that, right? I would go over clicker questions to kind of get a feel for some of the conceptual ones. And then just as best you can, try to even go over some of the old quizzes, kind of like a real quiz, kind of test yourself with it, in sort of real quiz situations. And then the discussions and the homeworks, right? I think some of those are useful. Yeah. What about, this is a good question. Anybody have other thoughts? Like some of you probably have been working in this class. Like what do you guys find has been helpful on the quizzes? Any study tips from your colleagues? Anybody? Nobody has a good study tip? Yeah, okay. It's just been tough business. All right. Other questions? Anybody have other questions or things they want to talk about? Yeah.
Can we go over how to do an RC circuit
with multiple what?
batteries.
An RC circuit with multiple batteries. Did we give examples of anything like that? Well, we go over the one from the last quiz, so would that count? Okay. All right. Okay, so let's just get started then. I just sort of picked out the quiz questions that were the hardest, or at least that people had the biggest trouble with. And so this was a popular one. So there's 3 charges. Why not? We bought the clickers, right? So there's 3 charges here, a negative, a positive, and a positive. And we want to know what regions is it possible that you'll have a zero electric field. And so we list out the different regions here, 1, 2, 3, 4. And so this one I thought was a tricky one. And so we're trying to find the place where the electric field could be 0. And so we had done stuff like this before, and so the way that we were trying to approach it was to okay, let's put yourself, so let's look at this point right here, for instance. So this region right here. So in this region, so I'll number these. So we'll call this charge 1, charge 2, and charge 3. And so the electric field, if you remember, points away from positive charges and towards negative charges. So if you look at this point here, and we just write out the directions, right? So we're going to be pointing towards charge number 1, away from charge 2, and away from charge 3. Right, so in that region right there, all the electric field contributions point in the same direction. So it's impossible that they're going to cancel out. Okay, so right there we know that that region 2 cannot be included. So we're going to sort of cross that one out. So that's the easiest one, I think, to cross out. And then if you look at the other cases, I'm pretty sure if you look at the other ones, like say, for instance, right here, in this case, so again, the contribution from 1 would point towards, and then the contributions from 2 and 3 would point in this direction here. So that's possible that it could cancel out. And then if we look at these other 2 points here, so like at this one here, so again from the 1 it would point like this. From number 2 would point like this, and then number 3 would point like that. And over here on this end, you'd have, what's that? So from number 1 again points this way. Let's correct that. So number 1's point this way, number 1 points that way, and then 2 and 3 point that way. So for sort of a first order approximation, so then the other 3 regions we can't completely cancel out. Okay, so what do you guys think as far as, are any of these regions you guys think are ones that would not be possible? Anybody got an idea, and why would you think that? Yeah.
Region 4 would be possible because the magnitude of the 2 quantum charges would exceed.
Yeah, so in region 4 there, you're always going to be closer to those 2 positives, and then there's 2 of them, right? So there's no way for the contribution of this one to cancel out those 2 because it's really far away, right? So that one there is another one that we can just cross out right away. And let's just sort of see where everyone was on this one. Okay, so I think we had the answer eventually. Yeah, so this one we could cross out too. And I think the other 2, you can't, those other 2 are ones that are valid. Okay, so the other ones, 1 and 3, like for instance, in region 1, you can get close enough to the negative charge, such that the electric field pushing this way will exactly equal from the 2 pointing that way there, and the same thing in between here. So again, I think that was a tough one that kind of encapsulated a lot of things about the electric field. Questions on that one? Okay, this is another one that I think sort of a related one that was tough. So let's see what we think about this one here. So we got the 3 or 4 charges, and we were asked what direction does electric force on charge A point due to all the other charges? And so talk about this one with your neighbors and see what you think.
So for region 3, why was the direction?
Okay, so I think let's look at this one. And I think the majorities here. Oh, okay, so this is definitely a good one to go over then. So again, just to make this easier, I'll number these. So I'll number 1, 2, and 3. So if we look at this, the force from 2 is going to be a repulsive force pushing up like this. That's the force from 2. And then the force from 3 will be an attractive force, and the force from 1 will be an attractive force there. And hopefully it makes sense that the force of 3 and the force of 1 are equal, and that magnitude is equal in those two forces, right? Because it's just sort of this, a similar picture. So right there, you look at that picture, and you can kind of look at and say, well, I can think it being up or down or 0, right? All three of those kind of make sense. So just like the last one, you got to kind of take another step. So can anyone argue up, down, or 0 from here? How would you think about it? Yeah.
I argue 0 because if you put it into like a force equation and then find the hypothesis, it's a K, B, and A for the system would be like grad 2. So when you put into the force equation, the K equal over grad 2B squared, which equal 2B squared, and multiply by 2. You just need to be the same thing as the opposite direction.
Okay, so I think if I'm gathering what you said, so what you're saying is, okay, if I look at the magnitude of force 2, I get K, and let's just call these two charged Q's or whatever, and then this would be divided by D squared. And then you're saying, well, if I look at force 1 and force 3, those would be KQ squared, and then what you said would be 2D squared, and that's because this distance here, if you make a little triangle there, right? So you've got D, D, and this would be radical 2D. And then I think what you were saying is, okay, so since there's 2 of these, and each one is half the same size as that, they should cancel. Is that kind of what you were thinking? Okay, so does anyone want to argue? Yeah.
If you like just added those two, you can see how they could cancel, but F3 and F1 have a horizontal component too. So when you add the two vertical components of those two, although they are pointing down, the magnitude pointing up.
Yeah, so I think that's a really good way to think about it. So your point is really great in that, okay, the actual magnitudes of these would add up to that other one. But if you look at what's happening is each of these two forces here, right, have an x component that's essentially being wasted, right? So each of those, F1 and F3 have like an x component that just cancels out. And so it's the y component that you're going to subtract from F2. And just because of the nature of how vectors work, the y component has to be less than that. So when you add those two y components together, they have to, by definition, be less than the F2. Does that make sense? So I'm glad you said that, because I think a lot of people were thinking exactly what you were there on that one. So everybody see that one there? So it's, again, it's a, like I said, I think a pretty tricky one. And, you know, the less we talk about that first quiz, probably the better. Still, sorry about that. But other questions on that one? Yeah.
So the x component of it cancels out, but with the hypotenuse, both hypotenuses for 1 and 3 also cancel out?
So like if you were, so again, this is one of those ones where it's like a 2A question in 2B, right? And so what we're trying to do is we're trying to look at all the forces on this negative charge. And so what we'd say is, okay, so the x forces cancel, and what would happen is the upwards F2 is bigger than the two forces down, and so in this case it would actually be accelerating upwards, right? And so the hypotenuses wouldn't cancel. It's like their x's would cancel, but their y's would be sort of taking a little bit from that F2, and then there'd be a net force upwards that you'd have, and so this thing would be accelerating upwards.
So it sounds like you ignore the hypotenuse in terms of the direction.
Exactly, because when it comes down to adding up forces, yeah, you in general want to break these all into like x and y coordinates, or some on some axis where you can then compare them with each other and sort of see what's actually happening. Right? This is a good example of why you have to do that, because when you just draw F1, F2, and F3, it's really unclear what's happening. Right? You got to be able to... Other questions? Yeah. Okay, everybody, please. Is it possible to make a problem like this where it would be 0? Oh, totally, sure. Yeah, I mean, but in this case here, it's not, right? And so we're just trying to focus on this case here, right? Yeah. But depending on how, we could, I mean, in this case here, to do that for this picture, you'd have to either change the distances or change the size of the charges or something like that. So in this particular case, it'll always be this way in this same kind of situation. All right, and so this was the other really nasty one from that test. Sorry, okay. I'm going to stop saying sorry. I do that a lot. It's something I'm working on here. So let's go through this one, because this is a good one to go through. And so what we have here is we have this situation where we got these two charges, and we're trying to find the total force. And I think just a lot of things were happening on this one to make it tricky. But the key thing that we want to do here is that we want to say, okay, my equation for force, my force is just the charge times the electric field. Okay, that's our, sort of one of our basic rules. And so here, I'm reminding you of the electric field from a long straight wire of charge where the line density of the charge is lambda, which is what we have here. So we have the electric field from that particular kind of charge setup, and that's the kind of thing that we found in class, and now we're actually using it. And I think one thing that was probably super confusing, you see these things afterwards, is that the distance here I called was r, but then the distance in the equation is r2, so that's probably super confusing. So I should have called this something different. And so maybe let's just go ahead and call that something different now so we can work on this together. We'll call this like x. So that's my x distance or something like that. Okay? And so what we tried to do here then is to say, okay, so what's going on is like the forces will only be in the x direction. And so my sort of force in x direction total would be the force on the positive minus the force on the negative. Okay, and so I'm going to sort of call this my positive direction going this way here. And you know what? I think, again, maybe that's another bad thing to call this. Let's just call this D, just to be really clear. And so this is like my positive x direction. And so if I look at my actual forces, if I'm drawing those out, okay, this is like a positive charge. And so the positive is going to repel this guy that way and attract that guy that way. So if you look at those two forces there. And so then just looking at it like that, then it would be more like that. So this one would be a negative, this would be a positive. And so what we do now is we put in this equation here. So it's Q times my electric field acting at the positive charge, and that's going to be a minus, plus Q times my electric field acting at the negative. And so it's negative Q. And this electric field is just this equation, so 2K lambda. Now down over here, okay, so D is the distance to the halfway point, and so I'm going to call this D plus A divided by 2. So that's the distance that I'm going to draw in between those two guys there. Okay, so does everyone see why we're doing that? So that, this R here is the distance from your wire, or this long straight infinite line charge to your charge. And so if I'm doing it from the positive guy, then this distance would be D, and plus this little thing would be A divided by 2. Okay? And then my next piece would be something along the lines plus q times 2k lambda. And then what would you guys call this distance in here? D minus a over 2. And so that's all good. And so the next thing that we wanted to do now is to add these two together. And so I did something kind of like this here. I pulled out the q, the 2, the k, and the lambda. And so another good thing to note is that is basically the physics 2b stuff, we're done with it right there. The rest is just kind of algebra, okay? And so maybe we should just pause and make sure everyone sort of sees what we did there. Any questions or concerns with that? Yeah. Okay. Yeah.
So we didn't define the like plus x direction. Will we have lost the y-axis?
I don't think so. I think we're pretty laid back. Like if you were able to go through and get everything right, and and weren't super clear with your definitions, but you still got it right. I think it's more like if you did that and then didn't get to the right answer, it might have been harder for the grader to see what you were doing. But yeah, I think we're pretty laid back with the grading. Yeah, at least we try to be. And so if I pull out those pieces, then what I have is and I'll rearrange it, is 1 minus d minus a divided by 2 minus 1 over d plus a divided by 2. And now the thing is, if you had left this as your answer, you would have gotten, or I guess, how did we do this? Yeah, so that's an acceptable answer to sort of what is the force. But the thing is we wanted to get it in terms of this other piece. And so what you can do then is add up those two pieces. And so to do that, I did something kind of like this. So 2k lambda q. And so I got basically a common denominator. Sort of like so. And so if we go back here, so I basically, took these guys here and said, okay, I want to add these together. So I multiplied here by d plus a divided by 2, and I multiplied here by d minus a divided by 2. And again, here I go doing it again, putting back those r's in. So again, this is just algebra. So I'm not doing anything physicsy or anything. And so again, just taking this and writing it out. And so then the last step, so 2k, or almost the last step, is then if I add these together, so up here I'm taking minus d minus a over 2. So if I kind of distribute that negative sign, I get negative plus a divided by 2. So the d part cancels, and I get a divided by 2 plus a divided by 2, which is a on top. And then down here, d plus a divided by 2, d minus a divided by 2. And the last step is I said, let's make the approximation that a is much, much smaller than d. So I can get rid of it here and get rid of it here. And so I get 2k lambda q, a on top, and then downstairs I get d squared. And so I think what this problem was asking for was the a to the m power. So the m power was 1, and the n power was 2. And we've done a similar one like this, but it was obviously, I think, a little bit different, and so it was confusing. Yeah, question?
Yeah, I just want to confirm, in the previous slide when we established negative f, positive, and plus f, we do negative f because the charge line is positive.
Exactly. Yeah. Other questions here? Anybody? Okay, so let's move on. So here's one from quiz 3, or the second quiz rather. This is probably the one, I think, the multiple choice that was the trickiest one here. So let's go ahead and see what we think on that one. I remember. Okay, and okay, so this is, so let's stop that and let's look at this. All right, so does anybody want to share what they were thinking on this one here? So first of all, if you want, you can always just do the actual math. And so I think some people did that. You can actually, you know, there's like a little grid here, so you can actually find the potential to 2 points and subtract them. And I think in the solutions for this, I did that. But you can also be just a little bit sneakier. So usually with these here, if you think about it, between these 2 points, so here's the point from there to there is that long, and the point from there to there is the same length. And so if I'm looking at the potential at the point y and the potential at the point x, I can, in a sense, forget about those two distances because they're going to cancel out, right? So I'm going to add up the total potential at y and the total potential at x, and I'm going to subtract them. And since it's the same charge with the same distance, I can kind of forget about that piece there. And so what I could do is a trick kind of like this is say, okay, so I've got that stuff. And so now I'll just draw my distances like this here. So here's this distance, and then here's this distance. And so I've got my Vy and and so we're going from point X to point Y. So my delta V is Vy minus Vx. And so are we thinking that this is positive or negative? And so what do you guys think about that? Is it positive or negative? Well, one way we can kind of think about this is do this relationship. So it's KQ. So I'll label these two distances. So I'll call this R1 and R2. And so for Vy, it's negative KQ over R1, and this would be positive KQ over R2 because the negative signs cancel, right? And so since the R2 is bigger, we could argue that this then has to be negative. So can everyone buy that? All right, and so because those two red distances are the same, we can focus on the other distance, the R1 and the R2, and then we can set up our sort of setup here and say, okay, so at point Y, I'm just going to forget about the contribution here, only think about the contribution there. And so it's negative KQ over R1, and this one is KQ over R2. And since R2 is bigger, I'm dividing by a bigger one here. That means the negative piece will be larger. I'll get a negative answer. Yeah. Say again? So because these are negative charges, so the equation for your potential is KQ over R. Since it's a negative charge, there'd be a negative there, just from the actual charge itself, yeah? Positive. Yeah, exactly. Other questions? And so then the last step to do this then is to say, okay, well then the work done, and it's a negative charge, so the work done by the electric field is defined as negative Q times delta V. And so for us it'd be a negative charge. Our charge Q is negative, and our delta V is negative, so 3 negatives equal a negative. And so this one should have been negative and potential difference of negative. Again, I'm kind of doing a sneaky way. You could have actually added up all of this stuff if you wanted to. And that would have worked just fine too. So for a lot of these, you can kind of do it that way. Questions on this one? Okay. All right, so now Gauss's law. And so this is the one from the test. And so charge is distributed uniformly throughout an infinitely long insulating cylinder of radius r. The charge per unit length is given to us as lambda. Use Gauss's law to find the magnitude of electric field at a distance r from the central axis. So lots of words here. But basically, we've got some cylinder. Okay, like this here. And what I want to do is I want to find the, for the first case, so this is cylinder of radius r, so we can kind of draw that over here. So this is radius big R. And so I want to find the electric field at some radius less than r, so we'll call it r right here. So for my Gaussian surface, I make a cylinder, and I'll make it here of length L and radius little r, sort of like that. And so I want to find Gauss's law to go through and do this here. And again, sort of, just to, you want to kind of talk about this stuff a little bit, sort of what we're actually doing. Ooh, I'm not sure if that's exactly what I wanted, but okay. So with the cylindrical symmetry, okay, basically our electric field is always going to be this way here. It's always going to be again 90 degrees to the surface and constant. Okay, because of this symmetry, it's always, you can't sort of pick any point on this cylindrical surface that's any different from any other. And so it has to be the same size of electric field, all right? And then because of the cylindrical shape to it, there can't be any sort of contributions sort of like left or right, okay? Because you can kind of think there's sort of enough charge on that side and enough on that side to cancel to make it always kind of pointing straight out or straight down like this. And so because of that, right, we get this thing where this side of the E dot dA business always works out to be E times, the area where our electric field is. And in this case, it would be the area just of this cylindrical surface. Okay, so for both A and B, it'll work out to be E times A, and that A is just going to be this area here. And so if this is, some radius r, and if we say call the length of your cylindrical piece L, then it's just 2 pi r times L would be that. So for both A and B, the left-hand side would be that. Let's see if I can transform back. Oh, good, okay. And then what would be the inside part? Well, that's where it's like a little bit tricky. And so for us, for the one we just did, so we'd say E 2 pi r times L. And so we've got charge per unit length of the sigma. And so how much charge we're enclosing, in this case, depends on our volume. Okay, and so we can go through and kind of do this here. Okay, so we'll say lambda times L which would give us sort of the total current here. And then what we want to do is divide by the ratio of these areas to give us only the current that's sort of in this little region here. And so what ends up happening is we get a lot of things canceling. And so the e to the r here comes out to be, maybe I'll switch back over here too. Just so we have more room. So e to the r, 2 pi r times L, and then lambda L pi r squared pi big R squared like that. And so the L's cancel. And this is, of course, divided by the epsilon naught guy. So 2 pi epsilon, and we get pi r pi big R squared. So I believe that, oh, actually those pi's cancel too. Okay, so questions on that one there? Yeah, question. So if you look over here, so I'm sort of taking the ratio, if we kind of look at this piece, here's this piece and here's this little piece here. And so the total current in here per length is that lambda. And the thing is we're looking just for this piece here. And so the way we want to sort of think about that distribution there is that it's the ratio of those two areas at that point. So the total charge at this point, right? And so the total charge, if we're looking, it's that charge per length, but then we're only including this small portion of it for the radius r. And that ratio for that would be like the cross-sectional area for that piece there. Other question, yeah? Yeah, thank you. There's a lambda in there too. So here's your lambda. Now, for the next piece, okay, so we do this next for something outside of the region. And so at this point, here's our guy with radius r. And so now we're making our surface outside, like so. And again, we're calling that radius r. And so it's the same left-hand side, e 2 pi r L. And then now it's just lambda times L. Okay, so there is no anything else because all that charge is in there, so we don't have to do that particular ratio. And so then the E is a function of R, and again, we've got to have this epsilon naught. It'd be 1 over 2 pi epsilon naught lambda over R. And one thing that you can always do to kind of check these is that in general, these things will be continuous at the point. So the point here where they switch over is when R is equal to R. And so if you look at this equation, right, if I plug in big R into that equation, I get 1 over 2 pi epsilon naught lambda big R over R squared, which equals 1 over 2 pi epsilon naught lambda over big R. And if you look at this one we just did, if I plug that in, I get the same thing. Okay, so you can always kind of check yourself to make sure that, because again, it's sort of tricky to kind of look at these afterwards. Questions on that, anybody? Yeah. So it's part of our definition. So our Gauss's law looks like this. So it's technically it's the E dot dA equals the charge enclosed divided by epsilon naught. And so it's just a constant that's in the definition of our equation. Other questions? Okay. Yeah. Sorry, we'll go back. What's the question?
What
Okay, so in this picture, we're looking for the electric field outside of this infinitely long cylinder of radius r. And so our r is actually the cylinder, and the little r is always the one for our Gaussian surface. In this case, the Gaussian surface is outside of our cylinder. And so the big R is the one that's smaller than the other one in this case. And so it basically switches between the two problems. Is that what you were asking?
Yes, for B is the answer the big R and small r.
So the answer would have been the small r. I'm just showing you that you can make them equal at that sort of boundary if you need to. Okay, here's another one that was missed by a lot of people. So this is from, I think, quiz 2 or quiz 3. So let's look at this one. So this is a parallel plate capacitor is charged by connecting it to a battery. The battery is then removed, leaving the charge on the capacitor plates. What happens to the energy stored in the capacitor if a dielectric with dielectric constant is inserted between the plates? So what do we think about this one here? Okay, what do we got here? Okay. So with these kind of problems, so the first thing you want to do, at least for me, is think about, okay, so what is staying the same with your capacitor? So basically, either the potential or the charge stays the same. And so here, you're removing the battery, and so we tell you, leaving the charge on the capacitor plates. And so that means that charge can't change. Okay, so that charge has to remain the same. And so we can look here and decide what happens to our potential, for instance, or something like that. Or say, so in this case here, the charge stays the same. What happens to our capacitance when we insert that dielectric with kappa bigger than 1? Does it increase or decrease? What do we think? It increases, right? So this capacitance increases, which would mean that our potential across there decreases, okay? And for us then, what was nice is we take, so there's generally a couple different equations that deal with the charge and the capacitors. And so here, since the Q stays the same, okay, and I know that my C increases, we can think of this here is that the U has to decrease. Okay, so it decreases. Now another way to think about it, it's always good to have different ways to think about it, is so our potential decreases, right? Well, if our potential decreases and the distance between the plates stays the same, then the electric field has to decrease, right? And if you remember when we talked about these dielectrics, we said that when you insert it, they basically work to lower the electric field inside your capacitor. And so when we talked about capacitor, we sort of talked about that the energy is stored in that electric field. And so if you're decreasing that electric field, that's another way to kind of think about it. So usually you can get, hopefully, 2 different ways to kind of think about these ones. Questions on that one? Okay, so this is another one that was nasty from quiz 3. So let's see what we think about this one here. Okay, so let's see what we're thinking with our friends. Okay, so this is good. So I think, okay, so this one looks like we have the right idea. And so what's happening here is we're increasing, or we're adding this extra B, okay? And typically, and so this was actually like the problem before it dealt with an ideal battery. And so here we're saying that in real life, a battery has a little bit of resistance to it. And so that's another thing to kind of consider. And so we're considering what that does. And we sort of invited you to think about it this way, but it's always hard, you know, to be invited to think on a test, right? But so you can rewrite it this way here, okay? And so you have this extra R. And so what happens is, the way I would explain is when you close this switch, you're giving another path for the current to come through B, okay? And so if you give another path, that means the current leaving here is going to get bigger. If the current leaving here is bigger, then that means the voltage drop across R gets bigger, which means the voltage drop across A has to do what? Get bigger or smaller? Smaller. Why does it have to get smaller? Anybody? Because so if it's my favorite 12-volt battery, then when we go up 12 volts, when we go down here and go down here, we've got to go down 12 volts. And so if the voltage drop here increases, then the voltage drop here has to decrease. And remember, with brightness, we can think about it as either being current or potential drop across it. Okay? And so again, just to kind of reiterate, here the current times R would increase, because the current coming through here would increase. So this voltage drop here would increase, which means the voltage drop on A has to decrease. Okay, so now in real life, you know, usually what will happen is that, you know, that R is tiny, and so that it's not that perceptible, but it does actually happen. And so this would be the brightness would decrease, but not go to zero if we're considering this. Anybody have a different way they thought about it? There's always lots of ways to think about these ones. Anybody want to say what they were thinking? Okay. So yeah, I think that I thought that was a hard one. Okay, let's try this one here. So you've got a current carrying loop next to a wire with current I going through it. Okay. Let's see what we got. Okay, so lots of different ways to think about this. Who wants to tell me what they were thinking on this one? Yeah.
So I did the right-hand rule first,
Uh-huh.
but I also thought that since both currents are pointing in the same direction, and both currents are half, then the net opposite force has to be pointing downward.
Okay, so it's a great way to think about it. So like currents attract. Now, so why would you say that that has a bigger influence than the one on top that's going in the other direction? That would be repulsive. Yeah.
Close to distance, so since that current is so much closer, I thought it would have a greater impact, but you could also do direct cancel.
Yeah, that's exactly right. What about the two side currents on the left and the right? What are those ones doing? Does anyone know? So they're pointing like opposite directions, right? If you actually look at the right-hand rule, and since those are the same distance, okay, it's going to be that they just completely cancel out. So I agree with this here. And so, just everything that was just said is great. But just to reiterate, too, just to kind of, so if the current is going this way, it's coming out of the page on top. And so if we do our force right hand rule, if I go with the current coming out, you can see that the force would be pointing down. So this one here, pointing down. This one's pointing up, but it's smaller. And then these two would be pointing this way and this way, but in the same direction, the same size, and so they would cancel. Questions on that? So we did pretty good on that one. Okay. Okay, RC circuits. So let's look at this one here. Okay, so when we talked about this in class, we said that for an RC circuit, you can think about it at sort of right after 0. So the time right about at 0, okay, we can think about the circuit, or where the capacitor is basically being a bare wire. So the capacitor, the way it's a little sloppy, but the way that it kind of tries to stop current flow is by charging up. Okay, when it gets fully charged up, it blocks all current. And as it gets charged up, it sort of starts to block current more. So the current going through there reduces. But at time 0, all right, it's basically like a wire. And so it short circuits that bottom resistor. And so at that early time, then if we were to sort of rewrite that, right, it would look like this. It would look like basically a circuit like this. And again, this is one of those things where, if we'd given you this problem, you would say, oh, that's not that bad, but sort of getting to there, right? And so this is equivalent, if you make it the simplest circuit in the world, to the voltage and then the resistance divided by 2. Right, so you're basically, initially, because of that short circuit, you got the same circuit as basically 2 in parallel, which when you combine them is R divided by 2. And let's see, can someone, so it's 12 divided by 10, so it's 1.2 would be the current for that case there. So questions on that one? So this would be 1.2 amps. Questions, anybody? And then we were kind of just talking about it, but then when you do this in the later times, this is time going to infinity, okay, what that current does, or that resistor, is it basically acts like this. It basically acts like just a break in the wire. And so it just completely stops all current flow. And so the circuit you'd have at this point would be something like this here. And again, so if you'd sort of started with this, it's not too tricky. It's just sort of realizing that you can do it. And when I found the current in that case there, I think it came out to be like 0.9 amps for that particular circuit. And so we had learned sort of ways to interpret the current initially and afterwards. And then you can kind of imagine then, so what's happening is the current through R1 is going to start out high because it's basically, just if you look at sort of the current in this case and the current in the other case, you can see that it's decreasing. So the current through R1 would be decreasing. So for part 2, you can argue that there. Questions on this one? Again, RC circuit was something that people were asking about. Okay. And so just a couple pieces of new stuff here. So here's one that we haven't seen. This is not from a test. This is, so we have a circular loop of wire here. And we're told that there's a magnetic field. And so you got kind of the side view and the front view the magnetic field is increasing with a certain equation there, and we want to know what direction will the current flow in that loop. And so this is stuff from induction from a few lectures ago. So what do you guys think about this one here? Okay, so let's see what we got here. Oh, okay, contentious. Okay, so again, the way that I kind of encouraged us to think about this is you look at like a before and an after. And so before, maybe there's 4 lines coming out. And so this equation with time gets bigger. As time gets larger, the B field gets larger. And so at the next second, you'd have maybe like 5 lines coming through. Something like that, you know. And so you want to make this one look like the previous one. All right, and so what you would do is nature would want to induce a current that's making a magnetic field going in, which would be clockwise. And so that would be along with the direction B, as the majority was saying there. Questions on that one? And so let's just try another, since this is kind of fresh stuff. And so here's another one like that. So now we have, you know, so sometimes you think of weird things. And so here's a loop, and there's like a little mechanism here that basically is making this loop get smaller. And so it's sort of like pulling this line through and making the loop get smaller. Okay, what kind of current would be induced in this case here? Okay. So in this case here, I think people got this one, so that's good news. So I think the majority got this. So I agree with them. And so initially, maybe there's 3 lines going in, and as this thing gets smaller, there's 2 lines going in. And so what you want to do is you want to have a magnetic field going in, and that would be, if you look at your right-hand rule, clockwise. And so that's what that would be there. So questions on that one? Anybody? Okay, and so the last one is the stuff from the last lecture. So I wanted to do a problem there. So I gave a few problems from the book. But this is obviously the stuff that we didn't get a chance to talk about in discussion at all. So we have an LC circuit, consists of a certain capacitor, and then an inductor, which we call here a coil of 0.80 Henry and no appreciable resistance. At time equals 0, the capacitor has a charge of 5.4 microcoulombs, and the current in the inductor is 0. And so the one thing that they can really kind of trick you with this stuff is when the stuff starts. And so if you remember, here is the stuff we talked about. And so the general situation that we talk about most of the time is we talk about when the capacitor is charged up initially and the current is 0 initially. And so this picture is the same sort of picture that we're looking at. Okay, and so this is the kind of thing that, you know, this is a good thing to sort of have on your equation sheet maybe. And so we're asked, how long after time 0 will the current in the circuit be maximum? Okay, and so if you look over here, so there's two things that you get from this kind of picture. First of all, that there's this, it's oscillating, and so we're asking about when will the current be maximum. And so if you look here, the current is maximum sort of, if you sort of have one total oscillation here, sort of 1/4 of a whole oscillation. And so this thing here gives us our oscillation frequency, and that was kind of one of the key things you wanted to get at. Okay, so omega equals 1 over radical LC. And so if I go back over to here, and so anybody got a calculator? Might be good to kind of, so it's radical LC, and so this would be 1 over, so we put these two things in there. So it's 3.4 microfarads, and then 0.080 henries, and then radical. And so I want to say when I did this, I got like 1900, something like that. Anybody? 1900 going once, going twice, anybody? But I think it was somewhere in that neighborhood. And so now, okay, so what do we do? So this is the part that I tried to stop and talk about because it's the kind of thing that from 2A we probably have forgotten. And so the first thing is you would want to say the frequency. Well, the frequency is this omega divided by 2 pi. Okay, so anybody, I'm sorry, I forgot to bring my calculator with me. So what's that 1900 divided by 2 pi? Anybody got? 302, that sounds about right. So 302 is our frequency. So 302 hertz. And then the period is 1 over the frequency. So it's 1 over 302. So I think that's the last one we need to calculate here. So 1 over 302. Anybody? Okay. You make me pull out my cell phone in class. This is... Okay, so 0.0003. So something like that. Does everyone agree with that? And so that's the seconds, roughly. And so then, again, that's the time to go through one complete revolution. And so this question is asking, when does the current hit maximum? And so that would be 1/4 of this. And so we're looking in here for the period divided by 4, which again, if I pull out my cell phone calculator, I get the answer of 0.00082 seconds, which is the answer that we get there, 0.82 milliseconds. So questions on this? So we're using kind of our knowledge of how this thing oscillates, and then our knowledge of this idea between omega, the frequency, and the period. So omega is basically the frequency in a language that the sines and cosines can use. Frequency is frequency that we can use ourselves, so 302 hertz, so this thing is bouncing back and forth 300 times per second, and then the period is how long it takes to do one revolution. And then the last question for maximum current, our equation for maximum current ends up being something kind of like this. So I max equals Q max times omega. Okay? And so that's sort of one of our definitions. And so in this problem here, we were given both the Q max, which is our initial Q, 5.4 microcoulombs, and we know this omega. So it's 5.4 microcoulombs, and the omega of 1900, which is radians per second. And so when we do this, we get like 10 milliamps. And so that's just an example of the kind of question that like they're asking in the book for this kind of stuff here. Questions on that, anybody? Okay, so I'll be down here if you got more questions. We got lots of office hours the next 2 days, so please come by and ask for help. Okay, thank you.